Bernd is an expert on gasification that has been involved in several developments in this area at ECN. Now at TNO, he is responsible for the area of gasification, gas cleaning, and gas upgrading. Today, Bernd is going to present a work entitled Experience from Pilot Scale FT Production from Gasification. Bernd, the floor is yours.
Thank you, Florera. Yes, my name is Bernd Freudenel. I work at TNO, and the presentation of this morning is about Fischer Tropsch connected to a gasifier. The first findings there. One slide about TNO. TNO is a very large research organization, the largest in the Netherlands, focusing on many topics. And my group is part of the energy transition unit, where we focus on a CO2 neutral industry via various lines within my group, which is located in Petten. Within the flower fields, we focus on using biomass to replace fossil resources. And this can be in the form of heat, fuels, and chemicals. So, as I said, the topic of today is gasification towards Fischer Tropsch. Gasification is what I believe a workhorse for the energy transition. IEA Bioenergy published a report end of last year where we investigated how gasification can be applied in existing infrastructures, so existing industries, to convert them into biorefineries, utilizing their own waste streams, co-producing additional products. And one of the proposed pathways there is a Fischer Tropsch pathway. But it's a key technology in utilizing all kinds of undervalued resources. So from agricultural waste and forest residues to municipal solid waste and even to plastics. Can be applied in many different industries, power generation, refinery, steel making, but also for fuels and chemicals. We believe that gasification is a crucial technology in reaching large shares of green gas in the European gas infrastructure, which is really a hot topic today. And as a technology, it can also be deployed or used for developing the bioeconomy, where you focus on using biomass to produce fuels, chemicals, energy, but also the circular economy. And when you talk about municipal solid waste, you take in plastics, and gasification allows you to convert plastics back into the building blocks of plastics, so you can make virgin plastics again. And the last topic, it's also a key technology in the production of sustainable aviation fuel, SAF, via the Fischer Tropsch pathway. I think many of you will understand the problems we're facing with making all these sectors renewable or sustainable. There's a huge challenge there, and especially in the hard to abate sectors like aviation. It's very difficult to supply SAF in substantial quantities. The report in the top right is written by my colleagues from TNO. And basically this also underlines the importance of biomass approaches, not only to supply sufficient quantities of fuels like Fischer Tropsch, but also to be cost effective. They evaluated the various routes and compared biomass pathways to power to X, so using renewable energy, and compared it to fossil-based products. And basically, it's a very nice report. But what it states is that E-based systems tend to be 2.5 times more expensive compared to bio-based routes. So making all these products from power to X is going to be very costly, and the sustainable electricity is not yet there. So that's a huge challenge. And it also mentioned that if you want to make renewable kerosene via the power to jet pathway, you would require 1,000 terawatt hours by 2050 and 143 million tons of CO2, which is also a substantial amount. And the good thing is, in biomass, you both have a lot of carbon and a lot of hydrogen. So it's an excellent pathway to go to Fischer Tropsch. So going into the project, what I will be presenting is part of the BECOOL project. It's a collaborative project between the EU and Brazil. It's ending the end of this month. And basically what we looked at in this project with all the partners is the growth, cultivation of biomass, the harvesting, the logistics to get the feedstock to a plant, and then the thermochemical conversion via pyrolysis or gasification to go to Fischer Tropsch. We analyzed this on with models, but we also supported it with actual testing in the fields and also in the lab with gasification test. And TNO was part of the group that was looking into this thermochemical conversion, where we actually showed that you can convert biomass into Fischer Tropsch products, and the results were also used to validate our models. So what did we do there? We had several routes where we looked at in the project. So pyrolysis, producing a liquid, and then high temperature gasification to produce syngas. But at TNO we have an indirect gasifier, which is more medium temperature gasification, and we focus on utilizing the biomass directly, making a product gas, so not a syngas. It's rich in tar and methane. And then after removal impurities with tar removal or a water wash and hydrodesulfurization, we would go to a steam methane reformer. So make syngas out of the product gas, remove the CO2, and go to Fischer Tropsch, where we produce the liquids. The economics, as calculated by IEA back in 2019, would be between 20 to 40 euros per gigajoule. And our approach, we reached this high end of that specific range, and that's without any learnings so far. Looking into the mass and energy balance, the overall efficiency is about 45%, and the carbon conversion 34%. And this is quite typical for Fischer Tropsch processes. So what we did is we demonstrated with experimental work that it's feasible, that it's possible to do this, and it's actually quite unique. So I will show you the lineup that we have, and this was part of it was existing equipment, so the gasification and the gas cleaning and part of the gas upgrading, but everything from the steam methane reformer, which is from this point forward, CO2 scrubber, and the high pressure fuel synthesis, that was all newly built and fully commissioned by the end of 2021. So it wasn't tested before. And within the BECOOL project, we actually had 2 weeks of running an experiment to demonstrate this. So what we did there with quite a big team of people, we gasified first beechwood, which is our standard starting point. So we operated the gasifier, and in the meantime we prepared the upgrading, so the cleaning and the conversion, the steam methane reforming, CO2 scrubber, in order to get a syngas of good enough quality. And at the same time, we were starting up our fuel synthesis part with gas from the grid, and eventually we connected it to our gasifier, so on biosyngas, and demonstrated the feasibility. Then part of the collaboration with Brazil was also to look into bagasse, which is a abundant available feedstock in Brazil. And we had some pellets available, and on the 9th day we operated on bagasse and demonstrated that it's also feasible to use bagasse as a feedstock. And you can see in the top right the quality of the feedstock, or the sizes, and that's typically for our lab scale experiments. You need a good size of feedstock in order to be able to feed it. So here you have an overview of what we were doing. You see some days were longer, some days were shorter. Sometimes you run into problems and you have to solve those. Typically every day we operated on 5 kilograms per hour, and on the 9th day we ran on bagasse pellets. Our gasification temperature is roughly at around 820 degrees C. And we try to keep everything constant for the duration of the 2 weeks. So this is some of the results on gas upgrading. You can see after tar removal, so Milena, Olga, after tar removal, you see a typical gas composition. It's rich in CO, hydrogen roughly 20%, and there's still some toluene and benzene in there, and ethylene is quite high. Then after the gas cleaning, which is the hydrodesulfurization and sulfur removal, what you see happening is all the unsaturated hydrocarbons get saturated, so the ethane content increases. There's still some benzene and toluene in there, but after the methane reformer, where you make syngas, all these components are destroyed and syngas is produced, after which we remove the CO2 in order to have just the syngas going into the Fischer Tropsch. And you see the CO2 is completely removed in this case. So going into the Fischer Tropsch pilot unit, it's a reactor of 2.5 meters long with an internal diameter of 26 millimeters. It's externally controlled with a thermal oil because of the exothermal reactions taking place. Roughly about 1600 grams per hour of gas was going in, starting with the gas from the gas panel, and then later switching to biosyn gas. And you can see at the bottom right the pictures, the Fischer Tropsch catalyst, which is a low temperature cobalt catalyst, and the silicon carbide pellets, which basically form the inerts at the inlet to get a good distribution and heat up of the system. And it's also mixed with the catalyst throughout the length of the reactor in order to mitigate all the exothermal reactions. If you would only have catalyst, then you would overheat at one point and probably melt your catalyst straight away. Here you have some of the results on the 6th day. You see all the thermocouples, and it's going up. And when the gas goes in, you see exothermal reactions taking place with these peaks, and sometimes very high. And this is an effect of a change in gas composition, but also a change in pressure. So every time you increase the pressure in order to reach your higher pressure for your process, you see also that there's an additional thermal effect because more heat is developed locally with a compressed gas. So far, what we've seen is that the tests were running best at 8 bar G and roughly 200 to 220 degrees C. And this is a little bit on the results. So we produced 3.5 liters of liquid/wax hydrocarbons. There was 600 grams per hour biosyn gas going in with a typical CO conversion of 34%. If it would be higher, then you would have a lot more heat developed, and you probably would need a different reactor type. The selectivity to C5 plus was about 80%, and methane was still quite high, but it's because the catalyst we used had a relatively low alpha. So the experiences here, what we can conclude is that technically it has been quite successful running this complex system from all the units connected for the first time successfully. That was quite an achievement. We successfully converted beechwood and bagasse. We've shown that the gas cleaning is cleaning the gas to below ppm levels, so ppb levels. And that might still be not sufficient for Fischer Tropsch, but that's part of ongoing research. We've also seen that the steam reforming was capable of reaching the right hydrogen to CO ratio, which was a question we had because we did not include in our lineup a shift reactor. So we had to do it in the steam methane reformer by controlling temperature and adding steam. We've seen the conversion there to be over 99% for the methane, which typically means that all the other hydrocarbons are also destroyed. The CO2 removal was actually perhaps a little bit too good, going to below 0.1 volume percent. And we produced a nice amount of Fischer Tropsch liquids and waxes in those 2 weeks. So the learnings from this test, well, what we've seen is that the CO2 scrubber is over-designed because it's basically a 2-column setup, and the first column already the CO2 was removed. We've also seen that the exothermal reactions taking place in the Fischer Tropsch is quite tricky to keep them in balance. And we've also noticed that there is a carryover of amines in certain cases from the amine scrubber, where we remove the CO2, and that's something to pay attention to, because that will definitely destroy Fischer-Tropsch catalyst if you do not deal with that. So this work was made possible by quite a large group of people, which I would like to acknowledge here. And I think at the end we will have time for questions. Thank you.
Thank you, Bernd. Thank you for this interesting overview, trying to show the